Good morning, good afternoon to all of you. I welcome you all for the afternoon session class. In the yesterday's class, we were discussing the concept of deadlock uh, handling methods, right? So we have learned deadlock prevention in the last class. So in today's session also, we will try to learn few more algorithms related to your deadlock handling techniques. Okay, so let me share the slide to you first. Yes, so this was the last class concept we have come across, that is deadlock prevention. So it is one of the method for handling the deadlocks, correct? That is this methods of handling deadlocks, correct? The first point what it says, so we have to use a protocol to prevent the deadlock, okay, or we can use the protocol to avoid the deadlocks. That is what the first point in handling the deadlock says, right? So this is the first protocol we have learned in the yesterday's class, that is deadlock prevention, right? So we all know the four safety conditions, okay, sorry, necessary conditions for deadlock to occur, right? That is mutual exclusion, hold and wait, no preemption, and the last one is circular wait. So if all the three conditions, four conditions occurs in our system, then we can say that our system is under deadlock stage anta helbodu now, correct? So to perform deadlock prevention, what we have to do antandre, we have to make sure that any of these four conditions does not satisfy in our system, okay? So we have to make sure that one. So we have learned these things in the last class, how mutual exclusion cannot be satisfied in a system anta. By making uh, resources as shareable, we can avoid mutual exclusion anta. Ade tara, so next we have learned was hold and wait, how we can show that hold and wait condition does not satisfy in our system antandre, okay? So if any one uh, process request a resource antandre, so all the resources which are available in your system should be given to it, okay? That is a first method of avoiding hold and wait. So when you give all the resources to one process, means other there is no chance that other programs or processes will never hold the resource, right? That's how you can avoid hold and wait. The second one is, so you are not allowing the process to send a request for the resource if it is holding something in it. That is a second method. That's what the 2 points says here. These 2 points will say how you can avoid hold and wait in your system anta. Third one was no preemption. So in no preemption means, here also there are two ways you can avoid a no preemption technique. The first one is, if a process sends a request for the resource, and if that resource you cannot allocate to that requested process immediately, ಅವಾಗ ಏನ್ ಮಾಡ್ತೀರ ನೀವು, ಯಾವ್ಯಾವ process ಅಲ್ಲಿ ರಿಸೋರ್ಸ್ ಹೋಲ್ಡ್ ಮಾಡ್ಕೊಂಡಿರುತ್ತಲ್ಲ ಆ ಎಲ್ಲಾ ರಿಸೋರ್ಸಸ್ ನೀವು ಫೋರ್ಸ್ಫುಲಿ ರಿಮೂವ್ ಮಾಡ್ತೀರಾ ಫ್ರಮ್ ದ ಅದರ್ ಪ್ರೋಗ್ರಾಮ್ಸ್. That is the first method you can use for no preemption, okay, for avoiding no preemptions, okay, by making all the resources which are holding that resources, by removing those resources from the processes, okay. Next, second one is, if a process requests a resource, you have to first check whether the resources are available. That is the second solution I'm saying. Then you can easily allocate. If the resources are not available, what is the next thing is that antandre, you have to check whether the resource which one process has requested is held by the another process anta check ಮಾಡ್ಬೇಕು ನಾವು. If it is held by the another process, if it is also waiting, if it is executing, then no problem. but if the process which is holding one resource and if it is waiting for the another resource ಅಂತಂದ್ರೆ ಅವಾಗ ಏನ್ ಮಾಡ್ಬೇಕು ನೀವು, then you have to forcefully remove the processes, sorry, you have to forcefully remove the resources from all those waiting processes and give those resources to this requested process anta. So that's how you are not satisfying the no preemption condition, right? The last one is your circular wait. Circular wait means what? So you will be having some set of resources and every resources been allotted some unique integer number. Okay, now the purpose of using this unique integer number is you have to make sure that the processes will use the resource or will request for the resource in this order, and in increasing order only they have to request the resources. Okay, so here is an example we have took. So for tape drive we have given the number 1, for disk drive we have given the number 2, and similarly for printer we have given the number 3 anta. ಇಲ್ಲಿ ಏನಾಗ್ತಾ ಇದೆ, if we take some 3 processes, say P1, P2, P3 ಅಂತ ತಗೊಂಡ್ರೆ, so every process will request the resources in this order only. First it has to request tape drive, then it has to go to disk drive, and finally it has to request printer anta. Okay, in this order if we maintain, then circular waiting will not exist anta artha. That's how you can avoid circular waiting in your system. So by using these 4 methods you can prevent system from entering the deadlock state, right? So these were the last class topics which I have discussed. Okay, so in today's session we will discuss the another protocol which is used for avoiding the deadlock. Okay, how you can avoid the deadlock occurrence in your system anta. Okay, now observe the very first point here. This is the important point. How you can avoid the deadlock antandre, so you should have some additional information that so the process will request this resource in future anta ನೀವು predict ಮಾಡಬೇಕು. Okay, so if you predict, then according to that you are allocating the resources to the processes. Okay, so that is the first point says. So in deadlock avoidance technique we will be having some additional information, correct? That is regarding how the resources are being requested anta. So yavaga ಒಂದು process resource na request ಮಾಡುತ್ತೆ. Okay, so we will be predicting these things in advance. So the main intention of this one is to avoid the deadlock. So ಮುಂದೆ ಆ ಡೆಡ್ಲಾಕ್ ಆಗೋದನ್ನ ಅವಾಯ್ಡ್ ಮಾಡಕ್ಕೋಸ್ಕರ so we have to use this additional information. Okay, right. Next one. So second point is, so with this knowledge, okay, so how the requests are generated by the process and how the process will release the resources, the sequence. Okay, sequence of requesting and sequence of releasing of the resources. Based on this knowledge the system will decide, okay, whether I need to grant the resources to the process or whether I should not grant the resource to the process, and the system will decide based on this knowledge. So that's why it says system can decide whether or not the process will wait or the process will not wait anta. Okay, this will avoid the deadlock situations. That is another point in deadlock avoidance. So if we have this additional information, we can easily predict whether the process will wait or whether the process will not wait anta. Okay, right. Next, next thing is about a safe state anta. Okay, so you can expect the question to be asked as a definition. Define a safe state anta kelbodu nimige. So what do you mean by a safe state antandre, so whenever any process request for a resource, okay, if you allocate the resources to the process, okay, requested process, your system should not end up in a deadlock state. Okay, even after allocating the resources to the requested process, your system should be remain as it is. It should not enter to a deadlock state. Then such a state is called safe state anta kariti now. You can observe this. The third point, what it is saying, what is a safe state andre, a state is said to be safe yavaga is safe if we can allocate resources to each of the processes. ಯಾವ್ಯಾವ processes ನಿಮಗೆ ರಿಕ್ವೆಸ್ಟ್ ಮಾಡಿರುತ್ತಲ್ಲ ರಿಸೋರ್ಸಸ್ಗೆ, ಆ ಎಲ್ಲಾ ಪ್ರೊಸೆಸ್ಗೂ ನೀವು ಅಲೋಕೇಟ್ ಮಾಡ್ತೀರಾ ರಿಸೋರ್ಸಸ್ನ. ರಿಕ್ವೆಸ್ಟ್ ಮಾಡಿರೋ ರಿಸೋರ್ಸ್ನ ವಿ ಆರ್ ಅಲೋಕೇಟಿಂಗ್ ದೀಸ್ ರಿಸೋರ್ಸಸ್ ಟು ದ ರಿಕ್ವೆಸ್ಟೆಡ್ processes, and still our system is running normally. It is not entered to the deadlock state. Then it is called as safe state anta kariti. So this is very important. You can expect as a definition, okay, in your examinations. Define safe state or what is a safe state anta nimage kelbodu. Okay, fine, right. So the next thing is safe sequence anta. Sequence means it is the order in which the processes are allocated the resources and in which the processes are executed in the system. Okay, in which order they have completed their execution and they have released the resources. That order is called safe sequence anta kariti. Okay, now if your system is in a safe state, then only there will be a safe sequence generated for your system. Okay, if your system is not in a safe state, means you can never generate a safe sequence. That you have to remember. Okay, whenever your system is in safe state, then only we can get a safe sequence. Okay, you can see this within the angular brackets I have written here: P1, P2, P3, P4, etc., so on up to Pn. It means that, so this is the order in which the processes has completed their execution and they have released the resources anta. Andre first P1 has completed the execution, so it has released the resources. Second, P2 has completed the execution, so it has released the resources. Like that, the processes are coming out of the system anta. Clear with this? That is what a safe sequence indicates. It is the indication of the order in which the processes has completed the executions and release their resources. Fine, right. So you can expect a question to be asked like this. So define a safe state and safe sequence anta nimage kelbodu. So this is the definitions you have to tell. Okay, safe state means safe state, it is a situation where all the resources which are requested by the processes can be granted and still the system will be working normally and system has not entered the deadlock state. Then such a state is called safe state. Okay, next. And about safe sequence means the order in which the processes have executed and released their resources is called as safe sequence. Okay, hope the two definitions are clear to you people. Okay, fine, right. Next. So observe the diagram what I have written here. So this is a diagram which is indicating the safe state and unsafe state anta. So whenever your system is in safe state means we can say that it is not entering the deadlock stage anta artha. But whenever a system is in unsafe state, then you can see your system is going to enter the deadlock state anta artha. So that's what this particular diagram is trying to tell. So that is what it is written in the first point. A safe state is not a deadlock state. Andre ನಿಮ್ಮ ಸಿಸ್ಟಮ್ ಸೇಫ್ ಸ್ಟೇಟ್ ಅಲ್ಲಿ ಇತ್ತು ಅಂತಂದ್ರೆ it will never enter a deadlock state ಅಂತ ಅರ್ಥ. That's what it is indicating. But whenever your system is in a deadlock state, then you can easily say that the system is in unsafe state anta artha. That's what the point is highlighted here. Okay, hope it is clear. Right. So here is one small example which is taken in your book to explain these safe and unsafe concepts. Okay, so we have one resource here, that is tape drive anta one magnetic tape drives we have, that is one resource. How many resources you have of that, means how many instances you have of tape drive? There are 12 instances of tape drive anta kottidare illi. Okay, and there are three processes we have taken as an example: P0, P1 and P2 anta. So at a time 0, okay, some random time it is at time 0. So they have given how many processes they have resources, these three processes have requested anta nimage kottidare alli. And they have using that particular resources yav time alli when time is 0. So P0 is holding 5 tape drives, P1 is holding 2 tape drives, and P2 is holding 2 tape drives. So how many resources are available with us now? 5 plus 2 plus 2. How many resources are there now? 9 resources, correct? So total how many tape drives we have? 12 tape drives. So how many are remaining? How many are allocated? Can you tell? Please unmute yourself and tell. How many resources are allocated for all the three processes? Please unmute yourself and tell the answer. How many resources we have allocated here? 5 plus 2 plus 2. How much it is? 9 tape drives. So out of 12 tape drives, 9 tape drives we have allocated anta artha, correct? So that's why it is written here. So available resources are how much now? We have 3 resources which are available still anta artha, correct? And so they have given the safety sequence here. ಏನ್ ಹೇಳ್ತಾ ಇದೆ? So first P1 has completed its execution, so it has released its resources first. Afterwards, P0 has completed its execution, so it has released its resources. Finally, P2 has completed its execution, so it has released its resources. So this is the safety sequence they have given. Means in this order, the processes has completed their execution in a system anta artha. Okay, right. Okay, nodi. So that's what I have written here. First process P1 is allocated how many resource? ಎಷ್ಟು 2 resource na allocate ಮಾಡ್ತೀವಿ, correct? So 2 resource allocate ಮಾಡ್ತೀವಿ. After the completion of process P1, ಏನ್ ಮಾಡುತ್ತೆ process P1? The process P1 will release the 2 resources. Okay, so initially how many resources I have? We have 3 resources available. Once the process P1, after the execution, when it releases the 2 resources which it is holding, then how many resources are available now? How many new available resources we have? 3 is the old available resource, plus 2 is the new resources which are released by P1. So 3 plus 2 how much? 5. So this is a new available resources in my system anta. Next, so according to the sequence, which is the next process now, it is P0. Okay, so P0 holding how many resources here? 5 resources, correct? You can see. So 5 resources are allocated to P0. After the completion of process P0, it will also release the 5 resources. Okay, now observe this. How many resources are available now? So previously, how many resources were present? 5. Can you see here? 5. Plus how many resources P0 is released now? It is 5. So 5 plus 5, how much resources are available now in my system? There are 10 resources available in my system anta artha. So is it clear to all of you? Right. So last one. So according to the sequence, which is the process which is executing now at the last? It is P2. So how many resources it is holding? 2 resources it is holding, right? So that's why it is the last point is saying P2 is allocated the resources. After the completion, the process P2 will release these 2 resources. Okay, right. So how many resources were available previously I have 10 resources, correct? So now how many resources are released by process P2? There are 2 resources which are released by process P2 anta. So totally how many resources I have now? 10 plus 2 is equal to 12 resources. Is it clear now? Correct? So how many resources you had? 12 resources you had. Okay. So once the completion of all the processes, you must get all the resources back. How many resources you had initially before the execution? After the completion of execution, you must also get the same number of resources. That's what it is trying to say. So after the completion of all the resources, I had how many available resources? 12 anta artha. So initially, before the execution of the processes, how many resources I had in my system? 12. So is it clear? Right. So this, if like this, if you are executing your allocating the resources and you are executing your processes, then your system will be in a safer state anta artha. Okay. Otherwise your system will enter to the unsafe state anta agutte. If your system enters the unsafe state, means we can say that our system is under deadlock situation anta ನಾವು ಈಸಿಯಾಗಿ ಹೇಳ್ಬೋದು. Clear with this? Okay, right. Okay, now observe this. So to explain your deadlock avoidance, so we are using 2 algorithms. Okay, deadlock avoidance, they have 2 algorithms. First algorithm is called resource allocation algorithm anta karitare. Okay, so second one is banker's algorithm anta. So these are the 2 algorithms meant for deadlock avoidance. So this is very, very important. So in your examinations, you will be asked with one problem on this. Very definite question they will going to ask. Okay. So under deadlock avoidance, we have 2 algorithms. One is resource allocation graph algorithm. Second one is your banker's algorithm. Okay, let us understand one by one. Why do we need 2 algorithms, right? Let us understand that first. So resource allocation graph algorithm is used why anta ನಿಮಗೆ ಕೊಟ್ಟಿದ್ದಾರೆ first point ಅಲ್ಲಿ. Why we are using resource allocation graph? When we have single instance of resources. Okay, single instances ಅಂತಂದ್ರೆ ಏನು? So I have only one tape drive, I have only one printer, I have only one hard disk. That is called instances. Okay, if I have 2 tape drives, means how many instances we are having? We are having 2 instances of tape drives anta artha. Correct? Clear with this? Okay. So when you are using resource allocation graph antandre, whenever you have single instance of resources in your system, then to avoid deadlock, you are using which algorithm? Resource allocation graph algorithm you are using. Clear with this? Okay, that's what the first point says. If we have only one instance of resource, then resource allocation graph is used to avoid deadlock. Clear? So we all know what is a resource allocation graph, right? This was discussed in the last class. So can anybody unmute yourself and tell what is a resource allocation graph? ಏನ್ ಹೇಳುತ್ತೆ ಅದು resource allocation graph? Please unmute yourself and tell. What is the resource allocation graph? It is already done in the last class, correct? It contains vertices and edges anta ಹೇಳಿದ್ದೆ ಅಲ್ವಾ? What are the vertices indicates in resource allocation graph?
Processes and resources.
Yeah, right. So can you elaborate the definition? What is that graph indicates? ಏನ್ ಹೇಳುತ್ತೆ graph ಅದು resource allocation graph? ಏನ್ ಹೇಳುತ್ತೆ resource allocation graph? It contains edges, no? What are the edges it will be containing? What are the edges it will be containing? Already forgot. Yesterday itself I did know all these things. Can you see here? What are the edges it will be containing? Request edge and assignment edge. That's what it is containing, correct? Resource allocation graph, it is a graph which contains set of vertices and edges, where vertices indicates processes and resources, correct? So request edge means the process which is requesting for a resource, and assignment edge means the resource is allotted to the respective process. That is what the assignment edge indicates. Clear? So single dot indicates one instance of resource anta. Clear? Okay, let us come back to this again, resource allocation graph. Okay, so observe the second point. What it says, along with the two edges, ಯಾವ್ಯಾವುದು request edge and assignment edge. So in this allocation graph, we are also having one more edge that is called claim edge anta ಕರಿತೀವಿ. You can see that is written in the bold font, claim edge. Okay, now what does the claim edge indicates ಅಂತಂದ್ರೆ, so it is an prediction andre prediction indicates what? In future the process pi is going to request for resource rj anta artha. Munde some time in future time one process is requesting this resource anta ನಾವು predict ಮಾಡ್ತೀವಿ ಮುಂಚೆನೆ. That prediction is called as claim edge anta. ಆ prediction ನಾವು ಗ್ರಾಫ್ ಅಲ್ಲಿ ತೋರಿಸಬೇಕಲ್ವಾ? How do we show that in a graph? We are showing that in a graph using the claim edge. So that is usually written in a dashed lines ಅಲ್ಲಿ ತೋರಿಸ್ತೀವಿ. So you can see that. I will just highlight that point. A claim edge indicates the process pi may request a resource. Okay, in future alladu. Okay, in future that process will request the resource anta artha, and it is represented in the graph by a dashed lines. Clear with this? What does claim edge indicates? Okay, right. Okay, now in future, suppose at time t naught, okay, let us consider a time as time t naught. So in this particular time, you are predicting that at time t1 process pi is requesting resource rj anta ನೀವು predict ಮಾಡ್ತೀರಾ. Okay, now when your time reaches t1, your process pi is now requesting the resource rj. That's what the fourth point is saying. ಅವಾಗ ಏನ್ ಮಾಡ್ಬೇಕು ನಾವು? We have to convert that claim edge into a request edge ಆಗಿ convert ಮಾಡಬೇಕು. That is what the fourth point says. What it is? When a process pi request the resource rj, then we are converting that claim edge into a request edge anta. That is what the fourth point says. Okay, the ಏನು ಡಾಟೆಡ್ ಲೈನ್ಸ್ ಇರುತ್ತಲ್ಲ, ಆ ಡಾಟೆಡ್ ಲೈನ್ ನ ಕನ್ವರ್ಟ್ ಮಾಡ್ಬಿಟ್ಟು ಸಾಲಿಡ್ ಲೈನ್ ಆಗಿ ಬರಿತೀವಿ. ಅದನ್ನ ನಾವು ರಿಕ್ವೆಸ್ಟ್ ಎಡ್ಜ್ ಅಂತ ಕರಿತೀವಿ ಅಷ್ಟೇ. ಡಾಟೆಡ್ ಲೈನ್ಸ್ ಇದ್ರೆ ಕ್ಲೇಮ್ ಎಡ್ಜ್, ಸಾಲಿಡ್ ಲೈನ್ಸ್ ಇದ್ರೆ ಇಟ್ ಇಸ್ ಅ ರಿಕ್ವೆಸ್ಟ್ ಎಡ್ಜ್ ಅಂತ ಅರ್ಥ ಅಷ್ಟೇ. ಓಕೆ, ರೈಟ್. Last point is what? A request can be granted ಯಾವಾಗ? Only if converting the request edge to an assignment edge does not results in a cycle formation in your graph. Okay, ಈಗ ನೀವು ರಿಕ್ವೆಸ್ಟ್ ಮಾಡಿರ್ತೀರ ಒಂದು ರಿಸೋರ್ಸ್ಗೆ. ಈಗ ರಿಕ್ವೆಸ್ಟ್ ಮಾಡಿರೋ ರಿಸೋರ್ಸ್ ನ ನಾವು ಅಸೈನ್ ಮಾಡಿದ್ರೆ ನಮ್ಮ ಗ್ರಾಫ್ ಅಲ್ಲಿ ಸೈಕಲ್ ಫಾರ್ಮೇಶನ್ಸ್ ಆಯ್ತು ಅಂತಂದ್ರೆ, ಸೈಕಲ್ ಫಾರ್ಮೇಶನ್ ಇನ್ ರಿಸೋರ್ಸ್ ಅಲೋಕೇಶನ್ ಗ್ರಾಫ್ ಇಂಡಿಕೇಟ್ಸ್ ವಾಟ್? ಅವರ್ ಸಿಸ್ಟಮ್ ಈಸ್ ಇನ್ ಡೆಡ್ ಲಾಕ್ ಸ್ಟೇಟ್ ಅಂತ ಅರ್ಥ. ಸೈಕಲ್ ಫಾರ್ಮೇಶನ್ ಆಗಬಾರ್ದು. Correct? So that's what the last point is saying. Whenever you are converting the request edge ಏನು ನೀವು assignment edge ಆಗಿ ಕನ್ವರ್ಟ್ ಮಾಡ್ತಿರಲ್ಲ, if it results in a cycle formation, then you should not do that assignment, or you should not do such assignments ಅಂತ ಅರ್ಥ. Only if the conversion of request edge into a assignment edge, if it does not results in a cycle, then only you can assign that particular edge to the requested process anta. Cycle formation, if it is happening, then you should not assign the resource. If there is no cycle formation, then you have to assign the resource anta artha. So that's how you are avoiding the deadlock in your system. Okay, ಆ ತರ ನಾವು ರಿಸೋರ್ಸ್ ಅಲೋಕೇಶನ್ ಗ್ರಾಫ್ ನ ಯೂಸ್ ಮಾಡ್ತೀವಿ ಡೆಡ್ ಲಾಕ್ ನ ಅವಾಯ್ಡ್ ಮಾಡಕ್ಕೆ. Clear? So let us understand this with a simple diagram. So this is a diagram you can see. Okay, so in this particular slide I have taken two examples. One example is showing the safe state, another example is showing the unsafe state. Let us come to the left part of your diagram, that is this. Okay, so you can see this, what edge it is I am pointing here. Please unmute yourself and tell what kind of an edge it is. The edge which I am pointing through my mouse, what edge it is called?
Assignment edge.
Yes, assignment edge, correct. What edge it is?
Request edge.
Request edge. Now what edge it is? What edge it is?
Climb
Dashed
edge.
lines. Huh?
Climb edge.
Claim edge, correct. Okay, claim edge means what? In future the process P1 will request the resource R2 anta artha. That's what it is called as a claim edge anta karitivi. Okay, so it is shown that the system is in a safe state anta. Safe state anta helabeku andre eno? So there should not be any cycle formation anta. Cycle formation ಆಗ್ಲಿಲ್ಲ ಅಂತಂದ್ರೆ the given system is in a safe state. Cycle formation ಆಗ್ತಾ ಇದೆ ಅಂತಂದ್ರೆ it will be in a deadlock state ಅಂತ. ಇಲ್ಲಿ ನೋಡಿ, process P1 will request the resource R1 in some future time. To make you people understand this, I will take the time here. Just for your example purpose, I will take this particular time as a T0 ಅಂತ ತಗೊಂತೀನಿ. Okay, now when time is a T0, process P1 will request the resource R2 in future anta ನೀವು predict ಮಾಡ್ತಿದ್ದೀರಾ. Okay, fine. That's why we have kept a claim edge here. When time becomes 1, like this. Okay, now you are converting that claim edge to which edge? When time reaches T1, you are converting that claim edge into a request edge agi convert ಮಾಡಬೇಕು. Okay, right? Like this. Just a moment, I will show that to you. Now what edge it is which I have drawn from P1 to R2? What edge it is?
Request edge.
It is a request edge because at when time was T1, the claim edge is converted into a request edge anta artha. Okay, now can you see there is any cycle formation in the graph after converting? Is there any cycle formation? There is no cycle formation, correct? Let us try for this one also. So when time reaches T2, so we have predicted that process P2 will also request for the resource R2 anta ನಾವು assume ಮಾಡ್ತೀವಿ, predict ಮಾಡಿರ್ತೀವಿ. Okay, so I will just write this one also here just for the example purpose. Okay, this is when time reaches T2. So you can observe when time reaches T1, this claim edge is converted into a